All right, so we are starting 13.1. This is a 1 day lecture. So I can tell you before we start that the homework for 13.1 will be due when? Monday. Yeah, Monday at 9 a.m. Does that mean you go ahead and do your homework right now as I'm teaching the lesson? Some of y'all do that. If you're awesome enough to do that, and you make hundreds on your tests and quizzes, I am not going to stop you because that is a pattern that is successful for you. Hey, speaking of patterns, do you like that segue? Do y'all remember patterns? At the very heart of any mathematician's core, they are pattern seekers. They are people who seek out and recognize patterns. That's what a mathematician does. We try to find patterns. We try to generalize patterns. We try to use our patterns to predict. That's what a mathematician at their very heart is. So let's try to look at some patterns here and see if we can kind of become pseudo mathematicians, if not full-fledged mathematicians for the day. All right, let's try this out. I spy red apple. Then I spy green apple. Next I spy red apple. What color might next apple be? Green. Y'all recognize that pattern already, huh? Now, what if I told you that you are correct? Would you be surprised? No, you would be like, yeah, I know it's green, right? Now, what if I just gave you the first two? What if I just said red apple, green apple? Could you predict the next one is red? Eh, not with as much confidence, right? So to develop a pattern, we usually need to see at the bare minimum. The bare minimum is three. Okay, the minimum is three to recognize the pattern. Any fewer than that, and the pattern can be anything. But red, green, red. Okay, it could be red, green, red, 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 green, red, 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 green, red, red. But basically, it's our job, if we're trying to communicate a pattern to someone, it's our job to list enough pieces there so that the person recognizes the pattern. So the more sophisticated the pattern is, the more things that you need to list for someone to be able to visualize that pattern. Got it? But if it's a basic pattern, then that's good. Okay, let's jump straight down below. Now we have a numeric pattern, 4, comma 8, comma 12, comma 16. We call this a sequence, right? What does the word sequence imply outside of a math class? Just in general, the definition of the word sequence means what? Order. Order, right? It means something is going to follow something else in a precise order. The days of the week follow in a precise sequence, right? Monday, Tuesday, Wednesday. What comes next? See, there's three, and you knew the next. Right. We don't just say, like, this week, let's mix it up. Let's do Monday, then Thursday, and then Tuesday, and then Friday, and then Wednesday. We'll end the week on a Wednesday. How does that? We don't do that. There's a sequence. Same thing with most of the time, our schedule here. We go to first period, second, third, fourth, fifth, sixth, and seventh. Okay. Sometimes we mix that up for testing purposes, but for the most part, it's a sequence. Okay. So, do you all know what number comes next in the sequence? How'd you get 20? You can spot the pattern. We are increasing by 4 units each time. Plus 4, plus 4, plus 4. We call this an arithmetic sequence. An arithmetic sequence. It looks like the word arithmetic, but because it is an adjective, we pronounce it arithmetic. Arithmetic sequence. Okay, I'll put an accent on the E. What an arithmetic sequence is it increases or decreases by a constant. And when I say increasing or decreasing, I mean add or subtract. Okay, that's what an arithmetic sequence is. So yeah, if you spot the sequence, what's 16 plus 4? 20. What's 20 plus 4? 24. Okay. Now, here's another term that's going to come up. This is called a recursive pattern. What is a recursive pattern? It relies on the previous numbers. That's what a recursive means. You couldn't just jump from the 8 to the 24, could you? Because to get to the 24, you had to add 4, and then add 4, and then add 4, and add 4. Okay? It's called a recursive. Recursive means it relies on the previous numbers. How do you get the next number in this case? I just add 4 to the previous. How do you get the number after that? You add 4 to the previous, so on and so forth. That's called a recursive pattern. So we have an arithmetic sequence. We add or subtract to get the next number. And to generate that pattern, we do it recursively, as we say. Okay, let's jump up here to the top right. Ooh, shapes. Cookie Monster. Me imagine circle cookies. Me imagine triangle cookies. Cookie Monster. Like all cookies, all shapes. Circle, rectangle, rectangle, triangle, circle, rectangle. What comes next? Rectangle sideways, right? And what comes next? Triangle. And then, okay, so the pattern repeats. This would not be a very good one if we just listed the first 3, right? If we went circle, rectangle, rectangle, what come next? You wouldn't say, triangle, duh, right? You wouldn't say that. You'd be like, I have no idea what you're doing, dude. Your rectangle fell over, by the way. Okay? But we list more. The pattern is obvious, then we keep going. All right, let's look at the dice over here. Ooh, dice. Cookie Monster like cookie dice. Cookie in shape of dice. 2, 4, 6, 8. Who do we appreciate? Mathematicians. Mathematicians. No, 2, 4, 6, 2. What comes next? 4, and then 6. Yeah, what is? Can we test over this now, sir? Right. All right, let's come down here to the numbers. 3, 6, 12, 24. This is another sequence. Sequence has terms separated by commas. We call the things terms, and they're separated by commas. What comes next here?
48.
Holy moly. Wait, how are you getting 48? Slow down there, buckaroo. We're not adding anymore, right? You can try adding. 3 plus 3 is 6. 6 plus 3 is 9. Ruh-roh, that didn't work. What we're doing is we're multiplying by 2. Multiplying by 2. Multiplying by 2. Y'all are good at patterns. 24 times 2 is 48. 48 times 2 is 96. Okay? We call this pattern a geometric sequence. Okay? A geometric sequence is multiply or divide to get the next term. So an arithmetic sequence, you add or subtract to get the next term. A geometric sequence, you multiply or divide to get the next term. All right, very good. Predominantly in this section, we're going to be studying these types of sequences. And believe it or not, in BC calculus right now, we are studying what's called a geometric series, which is very closely related to a geometric sequence. So if you ever go on to take BC, like at a double dual in 2 years, we'll be doing this at the end of the year. And it's fascinating stuff. I love it. All right. How about this one? 1, 2, 3, 5, 8, 13. How'd you get 21?
Oh.
1 plus 2 is 3. 2 plus 3 is 5.
Oh my God.
3 plus 5. Oh, you're a genius. I think this is going to work. Yeah, 5 plus 8 is... No, 5 plus 8 is 21. Can you be my accountant? Let's see. 8 plus 13 is what? That's 21. Yeah. And then 21 plus 13 is 34. Okay. This is another sequence. This one is not arithmetic because we're not adding the same number each time. Okay? This one is very, 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 very close to a very, very famous sequence. If I back up and put another 1 in the front, does the pattern still hold? Yeah, because what's 1 plus 1? It works, right? If you put the 1 in the front, then this whole sequence right here becomes what's called the The Fibonacci sequence.
Whoa.
Have you heard of the Fibonacci sequence? It's named after Leonardo de Fibonacci. He lived in the town of Pisa. You ever heard of the town of Pisa?
Pizza?
Pisa. They have bad architecture there. That's where the Leaning Tower is. Yeah, oops, the Leaning Tower of Pisa. Well, anyway, Leonardo de Fibonacci studied this sequence that has a lot of cool applications. But apparently, this is how rabbits reproduce: 1, 2, 3, 5, 8, 13. It's the sum of the previous. Yeah, like instead of exponential, rabbits increase according to the Fibonacci sequence. Now, here's what's cool about the Fibonacci sequence. Have you ever heard of the golden ratio?
No.
No? Wow, where have y'all been living? Under a mathematical rock?
Yeah.
The golden ratio is called phi, Phi, and it's 1.613-ish. It is supposed to be the most beautiful ratio of length to width that is out there, that exists. In other words, our human eye really appreciates things that are in a golden ratio to each other, where the length is 1.6 times bigger than the width. People they have done studies where like famous celebrities that are considered to be beautiful by people, men and women, when they look at their facial structure, the height of their head is 1.6 times the width of their face. And people are like, wow, that person's beautiful. They have the golden ratio happening all over their face, right? Now, how is the golden ratio related to this? If you take the term on the right and divide it by the term on the left. So like right here, 8 divided by 5, if you look at that, and then you look at 13 divided by 8, so on and so forth. If you look at 21 divided by 13, if you look at 34 divided by 21, as you keep taking these ratios of the one on the right divided by the one on the left, they approach 1.613-ish. Okay, they get closer and closer to that magical number, and that magical number is phi, which is the golden ratio. You don't have to know that for the test, but it's kind of nice to know in life, right? So the next time you say something's beautiful, bring your tape measure along and say, let me measure. I'm going to measure the width of your face and the height of your face, and let me do some quick calculations on my TI-83 calculator from Minnesota, because it's on your phone. And oh my gosh, your face is 1.6 times longer than it is wide. You are so beautiful. And they're like, okay, can I get back to my grocery shopping now? Because you stop them in the grocery store, right? Oh my gosh, you're so beautiful. Hey, I bet if you took a can of beans, speaking of beautiful, I bet if you took a can of beans from the grocery store and you measured this and you measured this, I bet that the height would be approximately 1.6 times the width. I bet it would be.
Do you know anybody with that?
Like personally,
Yeah.
my wife.
No.
Yeah. I mean, I had to measure her face before I proposed to her, but it worked. Yeah, she made the list. Um, golden ratio. Oh, you're thinking of food now, aren't you? Golden ratio face. Ah, there we go. Angelina Jolie, 1.618. So I was off a little bit. It's not 1.63. It's 1.618. Longer than it is wide. So look, there you go. Angelina. You thought I was just messing with you, all right? It's true. Oh, look at this guy. Oh, look at this guy. That dude is beautiful. Yeah, no, the guy from Breaking Bad. Angelina Jolie, I imagine. Oh, no. There's the real. If she was to be beautiful, look how she would look. Oh, man, maybe she doesn't have it. Oh, maybe Rihanna has it, the golden ratio. Maybe Rihanna. Yeah, Rihanna might have it. Oh, maybe Jack Nicholson. Does he have the golden ratio? Yeah. Anyway, I'm not lying to you. You could do more research on this if you want. But like if you look at the Parthenon, you know the Parthenon?
No.
Where have y'all been living? Not in Athens, Greece, that's for sure. The Parthenon in Athens, Greece. Guess what? People look at the Parthenon and they're going, that's freaking beautiful. Oh my gosh, stop at that picture right there. I'm screenshotting. Oh, I missed it. Ah, it went away. Oh, I got it. Cool. There we go.
So beautiful.
Guess what the proportions of the Parthenon are? The golden ratio. it is 1.61 times wider than it is tall. That's why when you go to Athens, Greece, you're like, I've never seen any structure so beautiful as this one. And your brain is naturally trained to think that. You're like, oh, that's just freaking beautiful, man. You don't say pretty. You don't say gorgeous. You don't say handsome. You say it's beautiful. It's the golden ratio. Well, right? Yeah, right on the heels of that. Yes. Yes. Yeah. Measure the proportions of the stall door. See if it's a beautiful stall door. Yeah. No, she won't. She doesn't even have a tape measure. All right. So let's jump into the notes now that we've talked about it. We got off subject a little bit, but it was worth it. The geometric sequence. Okay, so let's read. A sequence is a set of numbers related by a common rule where order matters. I'm going to add that, right? Y'all gave me that word. Order matters. Okay? More formally, a sequence is a function whose domain is the set of positive integers. Positive integers. So here's what we do. When we have a sequence like this, let me move that down. We call this term a sub 1. We call this term a sub 2. We call this term a sub 3, so on and so forth. This is a sub, guess what? You'll see the pattern 4. So the A's are the terms. So if I keep going like this, I would call this a sub n, a sub n, a sub n. N is a positive integer. And what it does is it just keeps track of which term we're on in the counting sequence. So a sub 15 will be the 15th term in the sequence. A sub 100 will be the 100th term in the sequence. Okay? So the domain is the set of positive integers, and the range are the terms themselves, a sub n. Okay? All sequences start with what's called an initial term. Initial means beginning, right? So a sub 1, that's always the first term, a sub 1. And the nth term is a sub n. We call this the nth term. Somewhere down the line, right? Somewhere down the line. Now, here's the important thing about a geometric sequence. We already said up here that this second one was geometric because to get from one number to the next, what did we do? We didn't add, we did what? We multiplied, okay? And you could divide too, it'd still be geometric. So we call that number, we call it the ratio. So in the example above, R was 2. The ratio was 2. Now why do we call it a ratio? Because to find the ratio, all you got to do is what we were doing over here with this Fibonacci sequence. You take the one on the right and you divide it by the one on the left. You take the one on the right and you divide it by the one on the left. You take the one on the right and you divide it by the one on the left, and you get your ratio. Okay? It's 2 all the way down the line. That's how you find your ratio. And that's why we call it a ratio, because it's the ratio of the one on the right to the one on the left. That's how you can find it. Now, you probably didn't do that. You probably just said, oh, 3 times 2 is 6, times 2 is 12. But if you wanted to find it, you can do 12 divided by 6 is 2, 6 divided by 3 is 2, 24 divided by 12 is 2, so on and so forth. So we call that the common ratio. Okay? Now, there's 2 versions of a sequence. If we call it in explicit form, this is the Holy Grail. It's very elusive, but if we can find it in what's called explicit form, we would love it in explicit form. Here's what explicit form is. It's the form of the geometric sequence that is a formula that's established the definition between the n, the input, and the general term a sub n, and its placement in the sequence. Okay? Which basically means we can generate any term at any time, any term at any time for any n. It's a formula, okay? It's an equation that we can use. So here's what it would look like. It would say a sub n, the nth term in the sequence as a function of n, is going to be the first term, a sub 1, times the common ratio raised to the n minus first power. Okay? Notice this right here, it looks exponential. It looks exponential. It has a variable in the exponent. So the reason this is a holy grail is because of this. If you have this equation and you want to find the 100th term in the sequence, let's say we want to find the 100th term in the sequence. All I have to do is take the number 100 and plug it into that formula, and presto magic, it spits out the 100th term. Now notice how much quicker that is if I had to do it recursively. If I had to find the 100th term in the Fibonacci sequence, I would actually have to find the 99th term. And to find the 99th term, I would have to find the 98th term. And to find the 98th term, I'd have to find the 97th. I would have to generate all of the terms from 1 up to 99 just to be able to find the 100th term. That's labor intensive, right? So that's the recursive sequence. If I can find an explicit form of the sequence, it's the Holy Grail. Okay? Now it says right here in a bubble, n minus 1 means the previous term. N minus 1 is the previous term. That's kind of common sense. If n is the nth term, n minus 1 is the previous one. Okay. We call r the common ratio. We call a sub 1 the initial value, and a sub n is the value of the nth term. Notice explicit form has an exponent. I already told you that. Okay. Now the other form I've already mentioned. The recursive form is it's okay. Spell it's better. It's okay. It's better than nothing. Better than nothing. Okay? It's a geometric sequence that establishes a pattern that refers back to the previous one. You need to know the previous one to generate the next one. It's okay. Here's what it looks like. The nth term a sub n is a sub n, which is the previous value, times r, right? So that would be like times 2, times 2, times 2. So that would be up here. The previous term would be 6, times 2 would be 12. And the next term, it would be the previous term 12 times 2, which is 24. And the next term would be the previous term 24 times 2, which is 48, right? So we write it in recursive form. The previous term, the previous value, I call it the previous term. Let's get in the habit of calling the things that are in the sequence terms. Okay, terms. That's what we call them later. Values is okay too. R is the common ratio. Okay, let's try example 1, now that we know. What is the common ratio for the geometric sequence? Identify the next 2 terms. Okay, so the good thing is they tell us it's a geometric sequence. That means to get from one term to the next term recursively, I have to either do what? Add or subtract or multiply, divide? I got to multiply or divide. That's what geometric means. Okay, multiply or divide. All right, 4, 6, 9, 27 halves. What a fraction. How do we find the common ratio if we know it's geometric? Right over left. Right over left. Right over left. Does it matter which right over left we use? The answer rhymes with go and starts with N. No. Very good. Either I'm good at giving clues or you're good at receiving clues. Or both. It could be both. What's 6 divided by 4 simplified to? 3 over 2, right? Which is 1.5. Okay. What is 9 over 6 simplified to? 3 over 2. Guess what 27 halves divided by 9 simplifies to if you go do state change flip? 3 over 2, yeah. You might as well choose the easier of the one, right? If you know it's geometric, if you absolutely know it's geometric, and this one said it was, just do 6 divided by 4. Make the number small, 6 divided by 4, it's 3 halves. Okay, so to generate the next term now, I got to multiply by 3 over 2. Let's do that off to the side. 27 halves times 3 over 2. Does anything divide out? Yeah, no, it doesn't, right? So if I multiply straight across, I get 81 over 4. So that's the next term in the sequence, 81 over 4. Boom. Now, how do I get the next one? What did you say, 3 over 2? Did you say add? Oh, times. If you add, I was going to be like, whoa, go back to the bathroom. Right? Yeah. That's doo-doo advice. You just leave your advice there and then come back. Yeah. But you said multiply or times. Yeah. So let's do it off to the side. 81 over 4 times another 3 halves. Does anything divide out? Oh, pooper scooper. I don't think so. So what's 81 times 3? 243 over 8. 243 over 8. Okay. That's a funky sequence. I'm not a big fan of those numbers. I hate to say that out loud, but that's it. That's a geometric sequence. It's a sequence because the order matters. We are generating the terms how? Recursively or explicitly? How are we generating these terms? Recursively or explicitly? We're
No,
recursively. We're generating recursively here. We're using the previous term and we're multiplying by the common ratio, which is 3 halves that we found by dividing right by left. And we're just multiplying. Now, if we kept going, we'd probably want to pick up a calculator at this point. I think I would, right? Okay. Questions on example 1? Hey, speaking of pattern, what comes immediately after example 1? Example 2? Yeah. Now we can get that pattern with only one example because we know, like counting terms in a sequence, a sub 1, a sub 2, a sub 3, that we're counting by positive integers. So we know that 2 comes immediately after 1, so on and so forth. That's how examples work. Okay. Determine if the geometric sequence given, so it is a geometric sequence, is written as an explicit rule or a recursive rule. Write the first 3 terms of each sequence. Okay, here we go. Letter A. A sub n is a sub n minus 1 times 6 with a sub 1 equaling negative 2. Is that recursive or explicit? That's got to be recursive. It's got to be. Here's how you know it's recursive. It relies on a sub n minus 1, which is the previous term, yes, yes? And it gives you an initial value. That's a giveaway for recursion. If it says with, and it gives you a starting point, you're like, I know the starting point. Now I got to generate the rest of them. How do I generate the rest of them? What am I doing each time? I'm simply multiplying by negative 2 is my starting point. 6, yeah, 6 right there. I was highlighting it. Yeah, 6 is the common ratio. So it means previous term times 6, previous term times 6, previous term times 6, previous term times 6. All right, let's write out the first 3 terms. So this sequence is going to be negative 2 to start with. And what's the next term if we go times 6? Negative 12. Good. And then times 6 again. No calculator here, right? Negative 72. Okay. And then, it only said the first 3. Thank goodness, because I don't want to do 72 times 6. 432. I don't know. Something like that. Whatever. Now, here's what we do. I put a comma, and guess how I show that the pattern continues on without me writing it? We put dot, dot, dot. Those are known as ellipsis points. That's the proper word for them. Ellipsis points. It means it keeps on going, yada, 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 dot, 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 so on and so forth. The pattern continues. Okay. Let's look at letter B. A sub n is 10 times 1 half to the n minus 1. With a sub 1 equaling what? No, it didn't say that. It just said, hey, if you want the nth term, booyah! Just plug in that value of n and calculate that term directly. There's no follow-up part here that says with a sub 1 equaling something, does it? So this has to be what? This is a explicit formula. If I can spell explicit correctly, let's try it again. Explicit. Sound it out. Explicit. 3 syllables. Explicit form. Explicit form. Okay? Explicit form. It's a formula. This kind of mirrors this. It looks kind of like this. Instead of a sub n, it looks kind of like f of x equals 10 times 1 half to the x minus 1, doesn't it? Yeah. So that's what an explicit form is. It's a formula. It's a function. Except instead of using f of x, we use a sub n. And instead of using x, we use n, where n is a positive integer. N is a positive integer. All right. It says to generate the first three terms. Okay, so what am I going to start with when I want to generate the first term? What value of n do we start with? 1 or 0 or 15? What do we start with? 1. 1. N is an element of the natural numbers. We call that n with the double bar n. These are your counting numbers. This is 1, 2, 3, dot, dot, dot. It doesn't include 0. It doesn't include negative numbers. These are your positive integers. We call them the set of counting numbers or the set of natural numbers. Double bar n. Like we use the double bar r for real numbers, the double bar n is the natural numbers. Okay, so we start with 1. So what's a sub 1? Plug in a 1 and you get, what do you get? 1 minus 1 is 0. Anything to the 0 power is 1. 1 times 10 is 10. There's a sub 1. Okay, comma. Now we got to plug in a 2. 2 minus 1 is 1. 1 half to the 1's power is 1 half. What's half times 10? 5. Hello. Now that's a sub 2. That's a sub 2. Ma, you can just put it right there on the table. Now I plug in a 3. 3 minus 1 is 2. That's 1 half squared. What's 1 half squared? 1 half times 1 half is 1/4. So we get a fourth of 10. Let's come over here. What's a fourth of 10? That's 10/4, which simplifies to what? 5/2. Hey, if I had to generate the next one, it's going to be kind of uncomfortable plugging in a 4. I don't mind having an explicit formula, because if I ask you for the 100th term right now, boom, you can just plug 100 in for n. It's going to be 10 times 1 half to the 99th power, whatever that is. We got the 100th term. But if I'm trying to generate the next term, I don't have to go back to the formula anymore. What am I multiplying by each time to get the next term? I'm multiplying by 1 half. That's your common ratio right there. Okay? So what would the next term be without plugging it into the explicit formula? What's 5 halves times a half? 5 5/4. And then the next term would be what? 5/8, so on and so forth. Yada, yada, yada. You see that? So sometimes it's easy to generate recursively. It's easy. Recursive is easy. It's just times a half, times a half, times a half, 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 times a half, times a half, times a half, half, half. But the recursive formula is the holy grail because, again, if I wanted the 100th term, I don't have to keep generating these terms recursively to get up to 100. I can just plug it in directly. So it's nice to have both. Yeah, you can too. Follow up with Riley's measurements on that stall door and just make sure it's the golden ratio. It wasn't a beautiful stall door? Okay, fair enough. Yeah. Do you need a tape measure? I'm just kidding. I'm kidding. I'm taking the joke too far. Beautiful stall door. No. That is the most beautiful stall door I've ever seen. All right. Example 3. Determine if the geometric sequence given. So again, we know it's geometric. Determine if it's written as an explicit rule or recursive rule. So we're doing that again. If the given rule is recursive, write an explicit formula. If it's explicit, write a recursive formula. Gulp. Now we have to write a formula? Given one, write the other? Given the other, write the one? It appears so. Let's see if we can figure that out together. You can sit right there. Thank you. All right. Letter A, number 3A. Is this explicit or recursive? It's explicit, yeah. Because I only have one formula. It doesn't say with a starting value of whatever. So it's explicit. So, would it be helpful to list out a few terms in order to figure out what the recursive pattern is, like we just did above? Times a half, times a half, times a half? Yeah, let's go ahead and do that. I'm going to put a sub 1 with an arrow. I like to label them. It helps me keep track of what I'm doing. What do I get when I plug in a 1 for n? 1 minus 1 is 0. 2 to the 0 is 1. Anything to the 0 power is 1. So I get 1 times 3, which is 3. There's my starting value. Gamma. Here's a sub 2. Plug in a 2. You get 2 minus 1 is 1. 2 to the first is 2. 2 times 3 is 6. Do you already know what we're doing to get from one to the other? Yeah. Remember in the formula, for the explicit formula up here, your common ratio is R, right there. Your common ratio is R. Mm, 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 mm. I like to hear a Skrillex version of that song. So the next one would be 12, and then 24, and then 48. Y'all got the pattern, right? Dot, 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 ellipsis points. Okay, so here's the recursive. Let's write the recursive. To get the nth term, we're going to take the n minus first term and do what with it? Multiply it by 2. Comma, oh, by the way, start with 3. Yeah, there you go. Yeah, times 2, times 2. So it's just instructions, right? Hey, to get the n minus first term, that's the previous term, times 2 gives you the next term, a sub n. Okay, there's the recursive form. Sweet. Let's look at the next one. Letter B. A sub n is a sub n minus 1 times 4, and a sub 1 is a half. Oh, yeah, this is, what you call this? This is recursive, right? It's got that and or the with, or, yeah, also there's a first term given. So let's list it. It's 1/2 is your first term. And what are we doing each time to get to the next term? What's your common ratio? Times 4. So times 4. I like to draw this little arrow. What's a half times 4? 2. Okay. And then the next one times 4. 8. Okay. I'm just going to put comma dot dot dot. Now, I want to write the Holy Grail equation. Is there a way to write an explicit formula so that we get that same pattern? Well, here's your template for writing the explicit form. It's this right here. If you can remember that, you got a template for writing an explicit form. What is it? It's the first term times the ratio that we've already identified to the n minus first power. It's important to do n minus 1 because when n is 1, that gives you r to the 0, which is 1, and it gives you the first term. So let's go ahead and do that. So the explicit formula is going to be the first term. What's our first term? 1/2 times, what's our common ratio? 4 to the what power? That's it. You're done. Boom. Hands free, right? You tied that calf's legs together and you're out of there. Calf roping. Comments, questions? So far, so good? Geometric is multiply or divide to get the next term. All right. Oh, look, we got 2 more examples. Can we squeeze them in? Write the recursive rule for the geometric sequence given in the tables. Write the recursive rule. It tells us it's geometric, doesn't it? So the first thing I'm going to notice is I am counting by ones. That's important. 1, 2, 3, 4, 5. Those are your counting numbers. Those are your natural numbers. Those are your positive integers. I know it's a geometric series. So how do we find the ratio? Is it right divided by left or left divided by right? So does it matter which numbers I choose? No. Guess what I'm choosing? I'm choosing the easiest two. 3 divided by 6, which is what? 1/2. My common ratio is a half. I keep taking a half, right? Half of 6 is 3. Half of 3 is 1.5. Half of $1.50 is 75 cents. Half of 75 cents is 37.5 cents, so on and so forth. Okay? So now I write the recursive rule. So here it is, the recursive rule. A sub n is, what's the first term? What are we starting with? Oh, sorry. The recursive rule. It's a sub n minus 1. That's how we start. A sub n minus 1 times what? 1/2. This is the recursive rule. Hey, you want to go above and beyond? You want to write the explicit rule too?
Yeah.
Why not? A sub n is going to be, it's the common base 1/2, or the starting number, sorry, 6 times the common base. I'm going to put 1/2 in parentheses because it's a fraction to the n minus 1 power. That's the explicit. You can just set her on this white table over here. There. All right, last one. Write an explicit rule for the geometric sequence based on the given terms of the sequence. Assume the common ratio is positive. Okay, so whoa, hang on now. We're starting with 2. That's a sub 1. And then we got a sub 2 is missing. Ay, Chihuahua. A sub 3 is also missing. What's going on? A sub 4, what is it? And then a sub 5, they tell us is 162. Okay. I noticed some missing terms, don't you? Can we figure out the common ratio if we have missing terms?
Yes.
Yes. How?
I don't.
You just being hopeful?
Yes.
Yes. Well, it's good to be hopeful. It's a good quality. Let's see. I would have to multiply by r once. I would have to multiply by r twice to get that one. I would have to multiply by r a third time. And I'd have to multiply by r a fourth time. Yes, yes? So I can make an equation out of it. So 2 times r to the fourth power should equal 162. Would you agree with that? I agree with that too. Okay, so now I can solve for r. Thus divide through by 2, that gives us 81. And now if I take the fourth root of both sides, I solve for r. What is the fourth root of 81? 3. 3. So now it says to write an explicit rule. So here we go. A sub n, this is explicit. It's a sub n equals the first term 2 times my common ratio 3. I'll just put a dot here because it's not a fraction. 3 to the n minus 1th power. Let's finish it up here with, well, we're done. That was perfect timing. Okay, so you have enough information. I was going to just do another recursive relation, but it didn't ask for that. Okay, so homework's due Monday. Sound good? All right. Go, gadget geometric